In this video, we're going to do some questions about quantifiers and then introduce the unique existential quantifier and do some questions with that. Okay, first question. We want to determine the truth values of the following statements. So, for n in integers, there exists an n such that n squared is equal to 2. Well, in this case, we know that n is going to equal plus or minus root 2. So, there is no n in the integers that when you square it, it equals 2. So there doesn't exist one, therefore this first statement is false. Okay, second one. For x in the real numbers, for all x, x squared plus 2 is going to be greater or equal to 1. Well, we know that x squared is going to be greater or equal to 0, no matter what real number we put in. So we have that 0 plus 2 is going to be greater or equal to 1. And this is true for any x we put in. So this statement is going to be true. Okay, third one. For x in the integers, for all x, negative x squared is going to equal x squared. So this is true or false. Well, let's put in a negative number, 0, and a positive number to see if this holds. Okay, so 0 squared is, of course, going to equal 0 squared. Okay, so that's good. If we take negative x, so if we take a positive number, so this is going to be a positive number, say 3, then negative 3 squared is going to be 9, and that's going to equal 3 squared, which is 9. Okay, let's take a negative number. So negative 3. Okay, so that's going to be positive 3. So 3 squared is going to equal negative 3 squared. And that is also true. Therefore, it is true for any x. Of course, I'm just taking specific examples, but we can see if we extend this bigger or smaller, it's going to be true for any integer. So this is also true. Again, I'm not asking you to prove this. I'm just asking you to determine the truth value. So we didn't actually need to take general numbers here and check. So you didn't have to take that negative a squared is equal to a squared. Don't have to check that. Just have to see if we can find a counterexample. We couldn't, so it's true. Okay, so here we're going to introduce the unique quantifier. So this says if there exists a unique x such that p of x, this exclamation mark means unique. So this means that there is exactly one. So there's exactly one x such that px. We need to determine the following truth values. So the first one says there exists a unique x such that x plus 1 is equal to 2x for x in the integers. So we can solve this and we can check. Okay, x plus 1 is equal to 2x. So we can subtract x from the right side, so we get 1 is equal to x. So the only solution here is x is equal to 1. So this means that there is a unique x, mainly 1, such that x plus 1 is equal to 2x. So this first one is true. Okay, what about the second one? There exists a unique x such that x is greater than 1, and our x values we can choose from are 0, 1, 2, and 3. So 0 greater than 1, that one's false. 1 is greater than 1, that one's false. 2 is greater than 1, this one is true. But oh wait, we have 3 is greater than 1, that one is true too. So this statement is false, because there is more than one x value that is greater than 1 here that we can choose from. So this x is not unique, therefore the truth value is false. Okay, third one is a nice exam question. So I just introduced the unique quantifier. You haven't done any questions on it before, so of course I'm going to put this on your exam because 1, you should be able to adapt to new quantifiers, and you should be able to reason about these things. So, which of the following statements are always true? So, if there's a unique x such that p of x, does it follow that there exists an x such that p of x? Okay, well, this one says exactly 1, and this one says at least 1. So if there's exactly 1, is there at least 1? And the answer is yes, of course. the first one, if there exists a unique x such that p of x, then of course there exists an x such that p of x. What about if there exists a unique x such that not px, then not all x px? So this says there's exactly one that's not p of x. Well, this says that not all x px. And of course, we can find logical equivalence here, so we know this is the same thing as saying there exists an x such that not p of x. And we can see that this, if we substitute p of x for not p of x, this is exactly equivalent to the first line, so of course this is true as well. So for instance, you may be asked to prove that these two are logically equivalent. That could be another question that could be asked. So we've shown that the first two are true. What about this last one? There exists an x, p of x implies that there exists a unique x, px. Well, no, this one's going to be false. So this one's not always going to be true. So I should say no, it's not always true, because there could be 1, 2, 3, all the way up to n out of n. So it could be 1 out of n all the way up to n out of n. And this says that there's exactly one x out of however many we have. So it's not always going to be true. Sometimes it'll be true, because sometimes exists an x will be exactly one case, in which case this will hold. But there's all these other possibilities that makes this not always true. So those were some questions on quantifiers. If you have any more, please leave them in the comments below, and I'll answer them the best that I can.